Hi, my name is George Smith, and I'm here to describe a theory of gravity that's completely contained within the Standard Model. First, let me set the stage. The starting point for much very successful gravity research achieved lately by one of the West Coast groups is that gravitons are dual copies of gluons. These physicists can calculate all kinds of wonderful and renormalizable things concerning gravity from their assumption that gravitons satisfied the so-called double copy property of gluons. Their unitarity method gave them equations that displayed a particular symmetry. Every term of their equations describing gravitons looked like the product of two gluon terms. But they have no clear theoretical reason why this should be. Here, a possible explanation is presented based on complex extensions of Lie algebras, an explanation that does not take us beyond the Standard Model, but uses an alternate partition of the Standard Model gauge space. Let me draw your attention to certain facts important to this presentation. First of all, some gauge theory facts. Gauge theories are constructed so that each type of gauge boson in the theory is coupled to one of the infinitesimal generators of the group of gauge transformations that underlie the theory. For example, the 8 gluons of quantum chromodynamics are coupled to the 8 generators of the underlying SU3 Lie group. We think of the exchange of a gauge boson, for example a gluon, as producing an infinitesimal gauge transformation associated with the generator it's coupled to. The finite gauge transformations that give rise to the phenomena associated with that gauge field are thought to be produced by the exchange of large numbers of gauge bosons coupled to the appropriate generators for that specific transformation. Probabilities are observables measured by experiments. Those measurements must be compared to the theoretical predictions, so the theoretically predicted probabilities cannot depend on the gauge used in their calculations. Thus, these probabilities must be invariant under gauge transformations. This will be the case if the finite gauge transformations are accomplished by unitary operators of the exponential type used throughout quantum mechanics. These operators will be unitary if their generators are Hermitian. Thus, we must require that the generators be Hermitian so that the probabilities will be invariant under gauge transformations. Now some Lie algebra facts. The structure of a Lie algebra is defined by its structure constants, and these are usually displayed by showing the commutation relations among the generators. The algebra's true form is revealed only when the commutation relations are expressed in terms of Hermitian generators. If the generators are not Hermitian, then the algebra is called a complex extension, and its apparent form can be very different from its true form. The true form of the algebra can only be revealed by re-expressing it in terms of Hermitian generators. Now let me give you the basic idea of this research. When two gauge bosons share a space-time history, they act as a single entity to generate gauge transformations which are compatible with that arrangement. First of all, let me define what I mean by the phrase sharing a space-time history. Two gauge bosons share a space-time history when they are at the same spatial location for each moment of their existence, from the moment they are simultaneously emitted to the moment they are simultaneously absorbed. This is not a bound state. There is no force involved. They are simply co-travelers for their entire history. The gauge transformations that this arrangement of gauge bosons generate belong to a different gauge group, and hence a different gauge field, than the ones generated by lone gauge bosons acting independently. Why is that? When two gauge bosons share a space-time history, they cannot act separately to generate gauge transformations. Therefore, the generators they are coupled to are no longer required to be separately Hermitian. That is, we lose the right to require them to be separately Hermitian. It is the sum of the two generators that must be required to be Hermitian, since it is the sum that generates the gauge transformations for two gauge bosons acting as a single entity as they share a space-time history. If we required the generators to be separately Hermitian anyway to guarantee the hermiticity of the sum, we might rule out solutions that nature might be using. But if the individual generators are no longer Hermitian, then the algebraic structure changes, as the original algebra becomes a complex extension of some new Lie algebra, whose structure needs to be determined by a transformation to Hermitian generators. These new Hermitian generators generate gauge transformations corresponding to the gauge field mediated by the paired bosons taken as a single entity. This will be easier to understand when we consider a specific case. Here you see the group that underlies the Standard Model. It contains the color SU3 of quantum chromodynamics, and it contains the weak SU2 cross U1 of the electroweak theory. I want to consider two SU2 gauge bosons from this group. Call them X and Y. They can be two SU2 gauge bosons from the electroweak part, or to avoid a difficulty later, they can be two gluons from the SU2 subgroup of color SU3. Since I want to consider them to be sharing a spacetime history, and hence acting as a single entity, I want to consider their combined algebra. Here you can see that X and Y each satisfy the easily recognizable commutation relations of SU2, with X and Y commuting since their action is in different subspaces of the now combined gauge space. If X and Y was separate and acting independently, they could generate independent gauge transformations, and we would have to require them to each be Hermitian. In this case, the compact semisimple algebra SU2 cross SU2 is realized, and this case is of no interest to us here. However, if X and Y are acting as a single entity by sharing a spacetime history, then we can only require their sum to be Hermitian. In this case, a new algebra is realized, which we must identify by expressing it in terms of Hermitian generators. On the next slide, I will define Hermitian generators J and K in terms of X and Y, and I will invert those definitions to get X and Y in terms of J and K. I will then put those expressions for X and Y into this algebra and work it down to a recognizable form. That's the program. So I define Hermitian generators J and K as linear combinations of X and Y. The expansion coefficients must be allowed to be complex so that Hermitian operators can arise from non-Hermitian ones. In this way, a complex extension of the algebra will be obtained, instead of simply a rewrite of the old algebra. The determinant, AD minus BC, must not vanish, so that X and Y can be expressed in terms of J and K. This is the inverse transformation, and we use these expressions for X and Y to re-express the algebra you saw on the last slide in terms of J and K. What do we get? This nice closed form for the commutation relations among all the components of J and K are what we sought. The mess is hidden in the cap A, B, C, D, E, F, but they're not too bad either. The question is, what algebra is this? More than one algebra has this form. To narrow the search down to a single algebra, we must apply the condition that the sum of X and Y is Hermitian. This condition gives rise to 4 cases, each with subcases. I show this in the accompanying paper. Most of the cases boil down to the SU2 cross SU2 case, which is of no interest here. The other cases boil down to the case of interest shown here. A star equals B, C star equals D. Before we look at the algebra that this case implies, let us note that if this case definition is put into the expressions for X and Y in terms of J and K, we find out that X and Y are Hermitian adjoints of each other. Instead of being self-adjoint, they are cross-adjoint. In this way, the sum of X and Y can be Hermitian without X and Y being separately Hermitian. Note that this case would have been ruled out had we insisted that X and Y be separately Hermitian. Okay, well, using this case definition, A star equals B, C star equals D, in the above algebra, it can be re-expressed uniquely as shown here. We recognize this as the algebra of the Lorentz group, or its covering group SL2C. This is important because in 1956, Udiyama showed that SL2C is the gauge group for the gravitational field. Thus we are describing a gauge theory of gravity. So what have we shown? Have we shown that gauge bosons share spacetime histories? No. What we have shown is that If two SU2 gauge bosons share a spacetime history, they will generate a gravitational field. This is our main result. Research directions. The next step would be to write down the Lagrangian, derive the Feynman rules from it, calculate all the tree, loop, and higher order diagrams needed to predict things, and check for renormalizability. Unfortunately, these things are well beyond my abilities. However, I think that this is essentially what the West Coast group has been doing with their double copy property of gluons. Here are some of their papers. These physicists have been calculating one thing after another and showing renormalizability for each calculation using the double copy property. They know how to do the calculations, but they don't have the theoretical reason why the double copy property should hold true. I think they have the how, and this work may describe the why. This work may describe the theoretical justification for the double copy property of gluons. Okay, let me give some cosmological consequences here. According to this theory, there was no gravity before the appearance of the gluon. The absence of gravity in the epoch between the Planck scale and the appearance of gluons, the QCD phase transition scale, should have profound effects on the expansion of the universe, since this is the epoch when gravitational effects are the strongest and retard expansion the most. In this theory, expansion would be unconstrained during this epoch, so the universe would expand much more than in conventional cosmological models without inflation. This would certainly necessitate modification of existing inflationary models. Replacing the Planck scale with the QCD phase transition scale, as this type of gravitational theory would necessitate, should also have profound effects on calculations of the cosmological constant. Presently, the calculated cosmological constant is 122 orders of magnitude greater than the observed value. This is considered one of the greatest unresolved problems of modern physics. However, a recent paper shows that the holographic principle justifies the use of a method of calculating the cosmological constant pioneered by Zeldovich in 1968, and that the predicted value so obtained is in agreement with the observed value when the QCD phase transition scale is used in place of the Planck scale. Thus, this theory, together with Zeldovich's method, would give the correct value for the cosmological constant. Finally, why should only SU2 gauge bosons share spacetime histories? If gauge bosons share spacetime history, shouldn't all gauge bosons share spacetime histories? Suppose gluons that do not belong to the SU2 subgroup of color SU3 share a spacetime history. The gauge field that these SU3 gauge bosons generate will be a complex extension of SU3 cross SU3, which, while being larger than SL2C, will contain SL2C as a subgroup. It will be some sort of generalized gravity that will contain the familiar SL2C gravity. Perhaps this generalized gravity can shed some light on dark matter and dark energy. That's all I have to say. Thank you for listening.